All right, time to start. Welcome, everybody. So we have Vladimir Khmelenko, our good colleague, dear friend. Vladimir is a research professor here in physics and astronomy at Texas A&M. And he is known for his leading role in the first experimental observation of the exchange tunneling reactions of hydrogen isotopes in the solid phase, and for the discovery and characterization of impurity-helium solids. He really worked in this field for a long time, and this is how he came up with those prominent seminal contributions to this field, defining the field in many ways. So he received his PhD from the Institute of Chemical Physics, Russian Academy of Sciences. And then he continued and he moved on and he received his Doctor of Science, which is the second PhD degree, the higher than the PhD degree in physics and mathematics from the Institute for Energy Problems of Chemical Physics, Russian Academy of Sciences. And this happened already more than 20 years ago in the second doctor degree. So this gives you an idea for how long Vladimir has been leading this field. So he received his second doctor degree for his work on matrix isolation and chemical reactions in condensed helium. And since 1998, for more than 25 years, quarter of a century, Vladimir has been working with David Lee, working with David at his group at Cornell University, and now he continues as our colleague at Texas A&M. He moved here in 2010, and he continues his groundbreaking pioneering research. And you'll hear the latest result of this research today. Vladimir, the floor is yours.
Thank you for a very nice introduction, and thank you for the opportunity to talk about our work. And I will talk about special quantum diffusion of hydrogen atom in solid H2 at temperature below 1 Kelvin. This work has been done here in the basement, and it's supported by NSF grant. And this work has been done by the collaboration of two groups. One group led by David Lee, and here Cameron Wetzel, it's a new addition of our new graduate student participating in this work. And this is a group from Turku led by Sergei Vasilyev. They very often visited us, especially when we have hard time with the fridge or spectrometer, because they develop a very nice spectrometer which we are using in our work. So this is the outline of my talk. First, I give some introduction in the field, really in hydrogen atom and hydrogen molecules. I will talk about recombination study of hydrogen atom in solid H2, focusing that all previous conclusion about diffusion, quantum diffusion of hydrogen atom has been done from the recombination measurement. Nobody really studied the diffusion when they create the gradient of concentration and make the observation of the movement of hydrogen in the gradient of concentration. It was early attempts of this study. I will talk about this. After that, I will talk about our experimental setup and provide results of these original studies of spatial diffusion of hydrogen atom at temperature below 1 Kelvin. And I will show the difference between the behavior of this diffusion in normal hydrogen. I will tell what it means normal and parahydrogen. And I will come to the summary. First, the hydrogen atom embedded in solid H2 represent a special class of quantum solids. What quantum solids are? This is the solids in which the 0.1 vibration, the amplitude of this vibration is maybe a few times smaller than distance between the atoms. And really, there is not a big class of these quantum solids like helium-3 and helium-4, H and H2, H2, D2, and that's all. Even neon is like on the H of this quantum solids determination. And hydrogen atoms are bosons, and usually question arises, is it possible to obtain VC of atom in solid phase? And when you can observe this, when you create the high concentration of this atom, so that the distance between atoms will be comparable with the de Broglie wavelength, which is determined by this formula. So when you reduce temperature, you can increase the de Broglie wavelength, and if they comparable, you can expect some quantum behavior even in solid phase for the atoms. And hydrogen has the electron spin and nuclear spin, and that's why the methods of electron spin resonance and nuclear magnetic resonance can be used for studying this system. And also hydrogen can move in solid phase through the matrix due to exchange-time reaction. It's shown here. So what happens in this reaction, the hydrogen molecule change their position, and this way hydrogen can move through the H2 matrix, and they can meet, these two atoms meet each other and recombine. And all information about movement of diffusion, this hydrogen atom, was obtained from this recombination measurement. And before our work, there was no experiment to measure spatial diffusion. I will tell quantitative, which gave in quantitative results from the measurement when H atom spatial diffusion by creating the gradient of H atom concentration in molecular H2. So I will talk about about hydrogen molecules. The hydrogen molecule can have a total nuclear spin 0 when two nucleus in a molecule opposite, directed opposite, and we call this para-hydrogen. And when the nuclear spins is aligned, this is a nuclear spin, the whole molecule is equal to 1. This is orthomolecules. And the wave function for the para-hydrogen is a sphere, and for the ortho-hydrogen, it's P-shaped, and ortho molecule inside para-hydrogen create defect, like shown here. So also the here it's shown the energy level for the molecular rotation energy level for the isolated para-hydrogen and for ortho-hydrogen. You can see the lowest energy level for ortho is 170 Kelvin higher. So it means, and also I will introduce what means normal hydrogen. Normal hydrogen at room temperature usually has 25% of para and 75% of ortho. If you send this normal gas into the cold sample cell and solidify this, because the lower state is para, it's the process of ortho-para conversion occur. And this is showing the fraction of the ortho molecule dependence on time. So it changed from 75% at the beginning to the 5% in 40 days. So there we will have this process ortho-para conversion if you have this normal hydrogen. How people making the para-hydrogen, they can cool down this hydrogen at the temperature maybe 20 Kelvin with the presence of the catalyzer, and it's this process of ortho-para conversion occur very fast. And after that, you can have a pure para-hydrogen, create a sample from pure para-hydrogen. In our experiment, we will call para-hydrogen the system in which 0.2% of ortho molecule, so very small quantity. Next, we will introduce the hydrogen atom in this molecular hydrogen. And I can tell you that there is the parameter, the Bohr parameter, which characterize the how quantum this solid. For hydrogen atom inside H2, this system has the largest the Bohr parameter. This is most quantum system which exists in solid phase. And we prove this hydrogen in our system by using electron spin resonance. So I will introduce the spin Hamiltonian for the hydrogen atom in magnetic field. It is shown here. It's interaction spin with magnetic field, electron spin interaction, nuclear spin with magnetic field, and interaction which will find interaction between the spins of electron and nucleus. The solution for the energy level for this Hamiltonian is known Breit-Rabi formula. We have 4 energy level for hydrogen atom. We always call this starting from lowest A, B, C, D states. And according to the selection rule, there are 2 allowed ESR transitions from A to D and from B to C. And it means that if you have spectrometer with the, some constant frequency and you will change magnetic field, you will observe 2 ESR lines for hydrogen. One is AD here shown and another BC. So this we will use in our measurement. We always measure this ESR line for hydrogen. And what information you can get from this line? From the line width of this line, you can tell about local concentration of these atoms. From the integral of this line, if you calibrate your spectrometer, you will know the total number of the atom in this system, in your sample. Now I will talk about early study of recombination of hydrogen atom in solid H2. How this measurement usually had been done? They create the system of solid H2, somehow introduce the hydrogen there. There are different ways to do this. But when they create the sample with atomic hydrogen in solid H2, for example, here, they wait and measure the quantity of this hydrogen in time. Usually they're using ESR and they're watching for the number of the spin in the system. And usually this process is a second order chemical reaction, and which describe this differential equation. And the solution of this is the one on a concentration is proportional to the linear proportional to the recombination rate. So if you reconstruct this like 1 over n on time, the slope of the curve will give you the recombination rate. In the 80s of last century, the studies of recombination rate has been done carefully in Moscow, Russia, in Kurchatov Institute. What they found, here it's shown that ratio of the rate constant at some temperature to the rate constant measured at temperature 4.2. And they found that in the temperature range between 1.3 and 4 Kelvin, this dependence of the rate constant linear, and at larger temperatures, it became exponentially grown. And they found that this part, they call this classical diffusion, and then this part is quantum diffusion. And they found that this quantum diffusion is linear dependent for this quantum diffusion rate of the constant of the hydrogen atom, linear dependent on temperature. At the same time, at the same organization, Kagan developed the theory of the quantum diffusion, and they predict this linear dependence. They suggest that atoms can be at low temperature considered like impuritons, and these impuritons can be delocalized, and they can freely move through the lattice with some zone like electron in the metals. But really they predicted this linear dependence on temperature. And barrier they considered, the barrier for the in crystalline field is 100 Kelvin approximately. And we call this physical diffusion, process of physical diffusion of the atom in H2. But later in Japan, Miyazaki and a group also studied the same things. They created the atoms by gamma radiolysis of solid H2, and they study the dependence concentration on time, and also have this curve, the same equation, but they explain this not like physical diffusion. They explain this that atoms diffuse due to exchange tunneling. So there is a barrier for chemical reaction H and H2, which is approximately 5,000 Kelvin, and hydrogen tunneling through this barrier, and when they meet each other, they recombine. And some period it was not clear which process is right, physical or chemical. And Commander in 2003 made experiment. So he studied the same process, the concentration on time, but at different pressures. This is at 0 megapascal, and also here it's at 10 and 13 megapascal. And he found that it doesn't depend on pressure. If this pressure will be applied to the physical diffusion, the barrier 100 Kelvin should be increased twice. So diffusion should be much slower. And you can see, according to physical diffusion, the rate of constant should become smaller. On this big barrier in chemical diffusion, it shouldn't influence. So after this experiment, everybody agree that the process of the tunneling is chemical in this H and H2. On this curve, we show the logarithm of rate constant on 1 over t. And if it's the dependence will be proportional to the t, we place all the result what we have in experiment for other group, and also place the green point where we decided to check this dependence at low temperature. And why we did this? Because if you consider this tunneling, you can expect that at low temperature, the rate of the constant will be slower. On this slide, it's a schematic mechanism for a combination of hydrogen atom and solid H2. This is combination of the potential energy and the potential for diffusion here. So this is two different places of atom in different lattice sites. You can see from here that when one atom somewhere here and another here. So when this atom and this atom is very far from each other, the tunneling is resonance. But when this atom became closer and closer, there is the mismatch between the level in the closest lattice site, and it means that tunneling should be slower. So at low temperature, the tunneling should be slower. We in 2006 performed this experiment first time. The rate of recombination atom at temperature below 1 Kelvin, and you can see here we make this graph 1 over concentration on time, and you can see the slope of this curve became smaller and smaller when you reduce temperature, and even at temperature 150 millikelvin, we even didn't see any recombination. So if you will place this point, what we receive on this curve, you will see at high temperature, it's somewhere dependence according to proportional to the temperature, but at low temperature, it's much slower. So we conclude that really this also supports its a mechanism due to the tunneling and the reducing of the recombination rate is due to the mismatch, more and more mismatch of the level in the closest energy level of the atom in the closest lattice sites. So, and we understand that what we are measuring and from this recombination rate, they determine the diffusion rate. The diffusion rate determined from this measurement is not characterizing the fastest movement of the hydrogen. They characterize the slowest when they move to each other, when it's the process is very slow. So, how we calculate the diffusion rate, because it's a diffusion limited process, and the relation between recombination rate of the hydrogen and diffusion coefficient, it's this one, when H0 is the latest parameter for the molecular hydrogen. In this temperature range, we place this logarithm of diffusion obtained from recombination on temperature. This diffusion coefficient in the range between 10 to minus 17 to 10 to minus 19 centimeters squared per second. And at the same time, it was known, for example, in the case of helium-3 in solid helium-4, their diffusion coefficient for this helium-3 is in the range 10 to minus 10, 10 to minus 7. So it's like 10, 12 order magnitude faster helium-3 moving in helium-4 than H in H2. And that's and when we compare this on the next slide, these two numbers, we understand that all this measurement not right. Because we are measuring the movement of the H atom, the slowest process in the movement of hydrogen. And our goal was to measure spatial diffusion of hydrogen atom by creating gradient of H atom concentration and monitor propagation of H atom in a bulk. So to have situation when this atom not go to each other, but they go in a place when this tunneling is resonance. But we were not the first who tried to study this special diffusion. In the middle, in 1985, group in Los Alamos made the following experiment. This is the ESR cavity, the most sensitive part of this cavity in the center. So they make the sample of molecular hydrogen in the center of this ESR cavity and start discharge on the side of this sample. They run discharge a few hours, and after that, after 4 hours, they saw the signal from hydrogen atom. This doublet is characteristic of hydrogen atom. When they waited 100 hours, they saw the signal became larger. So they proved that they saw, and the most sensitive part of this cavity is in the center. So they proved that there is spatial diffusion, but they didn't calibrate their spectrometer, and there is no any quantitative information, how fast it is, how slow. That's why we decided to develop method to study spatial diffusion of hydrogen atom, creating the gradient of concentration atom in the H2 and measure this movement of hydrogen. So I will start from our setup which we used. Usually we use the setup on a base of dilution refrigerator, which we use to cool down our sample. Our sample cell was placed in the center of the superconducting magnet, which can create the field 4.6 Tesla. And we use the ESR spectrometer. This is the cavity, Fabry-Perot cavity of the spectrometer. We use the dilution fridge. The sample cell was connected to mixing chamber to cool down. And also we had the, it's better that I will characterize the sample cell here. The sample cell, inside sample cell was the Fabry-Perot cavity, which contains a spherical mirror and flat mirror here. Also, we have two tubes. From one tube, we can send the molecular hydrogen. And from another, we have dissociator to send hydrogen gas, spin polarized hydrogen gas. I will tell you, we need this for calibration our method. And this flat mirror of the ESR cavity was a top electrode for the quartz microbalance. So we also can measure precisely the thickness of the film which you're making from the H2. So initially we grow the film. Usually we grow film with a thickness 2.5 micrometer. I will explain why later. After we created the film, we sent some quantity of the helium gas. Why we sending sending this gas? To start discharge, because the pressure of hydrogen at these temperatures, 10 to minus 15, you cannot start discharge there. So you send the helium, gaseous helium, start discharge, and when discharge is running, the electron created in discharge, and they bombarding the H2 sample and creating the atom inside on the surface of this sample. We know the energy of the electrons, approximately 100 electron volts, which allow to penetrate this electron on a width inside the H2, 100 nanometers. So this is our spectrometer, which was developed in Turku and bring to us, and it works perfect. There is a lot of part inside dilution fridge, which allow us to have sensitivity like 10 to 9 spins with a very low power, 10 to 20 picowatt power. We study our samples. What was our idea? Our Fabry-Perot cavity has the following distribution of magnetic field. We have a mode TM005. So we have this is antinode of millimeter waves. What it means, if you fill this sample cell with hydrogen gas, spin polarized hydrogen gas at this temperature, and apply gradient magnetic field so that you can see the resonance for each of these antinodes, you will see a maximum of the signal for the gaseous hydrogen. Our idea was to create solid film which cover two antinodes and create the layer of the hydrogen atom in one of the antinodes. And after that, using gradient of magnetic field and using our spectrometer to see when these atoms will come to another antinodes. It looks like a very nice idea, but when you place this thick film in the cavity, the frequency will be changed on 2.5 gigahertz. In our spectrometer has the bandwidth 1 gigahertz only. So it means that when you place this, it go out of the bandwidth of the spectrometer. So we built a special cell for this. So this cell allows to move a distance between the spherical mirror and the flat mirror in two ways. First, we have bellows here, which can move, change the frequency like 10 gigahertz. And also we have the piezo positioner, and this is bellows, which can fine tune of the frequency half of gigahertz. And here the cartoon of our sample cell. This is flat mirror, this is spherical mirror, this is the waveguide, and two tubes, which one for the H2, one to atomic hydrogen. But it was a problem. We never, after many tries, we couldn't create the big sample, thick sample, and be in a bandwidth of our spectrometer. So when we failed this, we understand at this moment we didn't find a way how to use this scheme of experiment. But we found that if we make in thin film, we can follow the propagation of the hydrogen atom in H2. So, and after that, our idea was to create the film. Here it's shown like a blue film with the thickness 2.5 micrometer. When we create this thin film, the frequency is, when we adjust the frequency of the spectrometer and make a film, it's still in the bandwidth of the spectrometer. We always can see the change of the wave, and having our opportunity for the cavity, we can adjust this resonator. So we decided to create a film first. After that, create this high concentrated layer of hydrogen by running this charge above. And after that, monitor propagation, watch your signal ESR. And now I will talk about experimental result. So what we see usually, as I told you, usually we see two ESR signal for the hydrogen. It's the low field and high field signal. And we see the kinetic of changes of these signals. The result for the, like red curve, it's result for the normal hydrogen, where 25 para is 75 ortho molecule. And blue is results for the para hydrogen. There is no ortho molecule at all. And there is shown the result signal after 2 days and shown signal after 7 days of accumulation. So what we create, we have the film. After that, we start discharge, and we continue experiment only making registration of the ESR. How change these signals? First, you can see the signal can be represent like some of the two lines. One is narrow line and one is broad line. What we saw after second day, the narrow line doesn't change in each of the experiment. Only broad line change. Also, we found that after second day, the line width of the broad line doesn't change, only the intensity increase. And I will show this in a follow slide. First, we study the process of accumulation. What information we can extract from our signals? First, from the line width of the signal, we can determine the local concentration of the atom, because the line width determines the dipole-dipole interaction of the atom. The more concentrated sample giving the broader line, and it's shown here. At the beginning of experiment, you have narrow line. Here it's shown the signal from the atom in the gas phase, and broader line is the signal from H and H2. When time progressed, the signal became broader and shifted. And from this broadness, we can find the local concentration. And second, we can find the total, we can calibrate our spectrometer and know the total number of the atom of the sample. How are we doing this? So we sending, when we have the sample, here it's shown this broad line on the left. It is a signal from H and H2. We sending in a sample cell the spin polarized gas. And we see the signal from the gas phase. When we create this sample from the gas, we use the saturation of this transition, what means spin polarized gas. So all spins are aligned, and this system is stable. But when you use the ESR transition, you are flipping the spin of the atom. And after that, this atom will recombine, because it creates molecule only when the spins are antiparallel. So this transition leads to the initiation of recombination of the atom in a gas phase. So if we initially make the registration of the gas phase, after that we saturate it and we measure the heat which released during this process. And we know that in each act of recombination, 4.5 electron volt release in one process. So when we, after this process, also measuring this signal from the gas line, we can know the change of the area, and we know how much heat was released during combination. We exactly know, can calibrate the number of atoms and the area of this signal. That's why we know exactly how much atom correspond this area. So we know, as I told you, and now we start to study. First, we study the process of accumulation, and here there is the dependence of the concentration on time for the normal hydrogen, red points, and for para-hydrogen. You see that they are coming to the same concentration. They saturated at concentration 1.2 multiplied 10 to 19, but for para-hydrogen, it's fast, like 5 hours. And for the normal, it's 2.5 days. It's different. I will talk later why we think it is. And after that, we study the behavior of the signal of from hydrogen atoms. First, this is concentration of total number on time, shown here. And here it's dependence of the local concentration on time. And you see after 2.5 days, it's saturated, and after that, local concentration doesn't change. Also, knowing that the line width determines the concentration, seeing the shape of this signal, we understand that we have two different regions of hydrogen in our sample. One region with high concentration, which corresponds to the broad line, and one region with a low concentration, which corresponds to the narrow line. And seeing on this curve, we developed the model. So we suggested that at the first stage, we create the high concentrated layer of hydrogen, and after that, concentration doesn't change. But because the total number is increasing, it means that this high concentrated layer move inside the bulk H2 film, and we can follow the speed of propagation of this high concentrated layer. So first we will analyze these two lines, broad and narrow, and this is the dependence of the number of spin for the determined from the broad line, and this is number of the spin or number of the atom determined from the narrow line. We decided it's small addition from the narrow line, and we analyze really by using one Lorentzian line, analyze only broad line in the following. But how we analyze? First, we suggested that the buildup of the concentration is according to this differential equations. N is the concentration of the atoms. K is the rate of the creation of this atom due to discharge. This is the decay of the concentration due to recombination atom, and this is movement of the spatial diffusion is into the bulk of this sample. Now, if we consider first dependence of the local concentration on time, we can consider the first stage when development of this high concentrated layer. We can neglect diffusion at this moment. In this case, there's only two first term in this equation will work. So we can find this solution, and we know this equilibrium concentration from experiment. And we can determine the rate of the accumulation from the slope of this curve. In this case, we can calculate the rate due recombination of the atom, and this rate from this particular experiment was found this one, and according to this equation, we can find diffusion coefficient due recombination, which will be equal around 10 to minus 19 centimeter per second. Next, we think that on the next stage, this increasing of the number of atoms due to propagation this high concentration layer into the bulk. So in this diffusion, due to the second Fick's law determined by this term of the equation, and how we can extract this diffusion coefficient. First, we know about our sample that total number will be equal local concentration multiplied on volume. Yes, local concentration in this second stage doesn't change. We know exactly how it is. We know the surface of our sample, our flat mirror where we create the sample. And we can determine from this curve, we can determine the penetration depth according to this simple equation. So we make the graph, the thickness of this high concentrated layer on time from the recalculation, and this is red points. And after that, we consider that this is should be diffusion, one-dimensional diffusion. So the solution should be a square root of 2 spatial diffusion multiplied on time. And this solution is shown here like a line. And from here, we can, from this fit, you can determine the spatial diffusion. And this is 10 to minus 16. So at the same experiment, we find a way to find diffusion due to recombination and diffusion due to spatial diffusion or penetration of this high concentrated layer into the H2 film. And the ratio of this coefficient, 375. So it's faster, it's much faster than diffusion due to recombination. So how we can see this, and also I didn't tell, we have always this high concentrated layer, which correspond to the broad line. But we consider that low concentrated signal from the front of this layer, and this is low concentration layer. And after 2 days, we have like distance 1.4, 0.14 micron, and after 7 days, we have 0.2 micron penetration of this layer for normal hydrogen. So after that, we decided to prove that we are right, and we understand that we can create the sample cell, thin sample cell, and if we have really this diffusion rate after some period of time, like 9 days, this high concentrated layer should come to the flat mirror and should recombine. So the concentration after some period should not change. I don't know, you believe or not. So this is dependence of the local concentration, as usual, is saturated. And this is total concentration. It's come to here, and after that, we think that it's stabilized or in penetration depth. So this peaks this influence of transfer helium in our Dewar on our amplifier of the spectrometer. But you see that when it's after relaxing, it goes to this level. Okay. So first, when we measured this, we decided to understand. We measured this in normal hydrogen, how it's influenced, how it will behave in a para-hydrogen. And this is result the same dependencies, local concentration of time A and total concentration on time on a B. And this is for normal, it's the same. I place this for comparison, and this is for para-hydrogen. As I mentioned before, the fast accumulation at the beginning of the para-hydrogen, and after that, it's saturated local concentration. And the total number in para-hydrogen, initially it's higher, but after 6 days, it became equal, and after that, it became smaller. This is again the same analysis of the kinetic of the changes of the spectra. And at the same way, we calculated the penetration depth for the this high concentrated layer in para-hydrogen, and it's shown here by blue points. And what you can see that really after 6 days or at the end, the penetration depth in para-hydrogen is slower than in normal hydrogen, which is like counterintuitive. We thought that in para-hydrogen it should be faster. And this is comparison what we have from the comparison in normal hydrogen and para-hydrogen. The recombination rate in para-hydrogen is faster, and corresponding the recombination diffusion obtained from recombination is also faster for the para-hydrogen, but spatial diffusion is smaller, 3 times smaller. How it can be? So we think that because the recombination rate in para-hydrogen is faster, because we are trying to follow the high concentrated layer, which is slow, because of recombination in para-hydrogen faster, some of the atom in this high concentrated layer in the para-hydrogen was died due to recombination, faster recombination. And I'm coming to the summary of my talk. We perform investigation of accumulation and pure spatial diffusion of H atom in solid H2 at temperature 0.7 Kelvin. We found that the rate of accumulation of hydrogen atom in para H2 film is 1 order magnitude faster than in normal H2 film, this graph. We also found that spatial diffusion proceeds more than 2 order magnitude faster as compared to diffusion obtained from the recombination measurement, this coefficient. But we also found that propagation of H atom high concentration layer in normal film faster than in para. It's shown this curve. What in future we want to do? We want to measure this process at the lower concentration. So if the concentration will be lower, like in the case of helium-3 in H2, the diffusion should be faster. And also, this approach, what we develop, can allow us to measure spatial diffusion, for example, the deuterium atom in solid D2 field. And as usual, we still have the goal to reduce temperature of our experiment much lower and try to continue search for a basic condensation of H atom in solid H2. And thank you. That's all I want to tell.